Okay, good morning.
Morning, sir.
Morning, sir.
Okay. ബാക്കിയുള്ളവരൊക്കെ ഓക്കെ, നമ്മുടെ പോർഷനൊക്കെ ഇപ്പൊ ഏകദേശം കഴിഞ്ഞു. പിന്നെ നമ്മൾ ചെയ്യാൻ ഉദ്ദേശിക്കുന്നത് മെയിൻ ആയിട്ട് നമുക്ക് ക്വസ്റ്റ്യൻ പേപ്പേഴ്സ് 3 സെറ്റ് ക്വസ്റ്റ്യൻ പേപ്പേഴ്സ് വരുന്നുണ്ട്. ഓക്കെ, അപ്പൊ അതിന്റെ എല്ലാവരും എത്തിയോ? ജസ്റ്റ് ഒന്ന് കാണിക്കാം ക്വസ്റ്റ്യൻ പേപ്പേഴ്സ്. നമുക്ക് 3 സെറ്റ് ക്വസ്റ്റ്യൻ പേപ്പേഴ്സ് നമുക്ക് അവൈലബിൾ ആണ് യൂണിവേഴ്സിറ്റി ഇതുവരെ നടത്താൻ. അപ്പൊ അതിന്റെ ക്വസ്റ്റ്യൻ പാറ്റേൺ നിങ്ങൾക്ക് ഷെയർ ചെയ്തിട്ടുണ്ട്. ഈ ക്വസ്റ്റ്യൻ പേപ്പേഴ്സ് നമ്മുടെ ഗൂഗിൾ ക്ലാസ് റൂമിൽ അതുപോലെ ഇൻവേസിലും ഉണ്ട് തോന്നുന്നു, ഇൻവേസിലും ഉണ്ട്. അപ്പൊ അതിനകത്ത് നോക്കിയാൽ അറിയാം. പാർട്ട് എ വരുന്ന ഈ രീതിയിലാണ്. പാർട്ട് എയില് ഓക്കെ, പാർട്ട് എയില് ഇതേപോലെ തന്നെ 4 ക്വസ്റ്റ്യൻസ് ഉണ്ടാവും. ഓക്കെ, അതിനകത്ത് ആൻസർ എനി 3 ഫുൾ ക്വസ്റ്റ്യൻസ്. നമ്മുടെ യൂഷ്വൽ പാറ്റേൺ, നിങ്ങളുടെ സാധാരണ പാറ്റേൺ തന്നെയാണ്. ഇതിൽ ഫസ്റ്റ് 2 ക്വസ്റ്റ്യൻസ് വിൽ ബി ഫ്രം മോഡ്യൂൾ 1 ആൻഡ് 3 and 4 ഫ്രം മോഡ്യൂൾ 2. അപ്പൊ ആ രീതിയിലായിരിക്കും ഉണ്ടാവുക. അതേപോലെ പാർട്ട് ബിയിൽ വരുന്നത് ഈ കാണുന്ന പോലെ 5, 6 ഫ്രം മോഡ്യൂൾ 3, അതുപോലെ 7 and 8 ഫ്രം മോഡ്യൂൾ 4. ഇനി പാർട്ട് സിയിലാണ് കൂടുതൽ ക്വസ്റ്റ്യൻസ് ഉള്ളത്. അതായത് 6 ക്വസ്റ്റ്യൻസ് ഉണ്ടാവും. അതിൽ ആദ്യത്തെ 3 എണ്ണം കറക്റ്റ് എന്തായിരിക്കും 5th മോഡ്യൂളും, അതേപോലെ അവസാനത്തെ 3 ക്വസ്റ്റ്യൻസ് 6th മോഡ്യൂളിൽ നിന്നും ആയിരിക്കും ഉണ്ടാവുക. ഇതെല്ലാം ആ ക്വസ്റ്റ്യൻസ് എടുത്ത് വായിച്ചു നോക്കിയാൽ തന്നെ അറിയാം നമുക്ക് ഏത് ലെവലിലാണ് വരുന്നത്. എല്ലാം എക്സ്പ്ലെയിൻ, കമ്പയർ, അതുപോലെ വിത്ത് ഹെൽപ്പ് ഓഫ് മിഡ് ഡയഗ്രം, വർക്കിംഗ് ഓഫ് ഷൂസ്, ഇങ്ങനെ ഈ രീതിയിലൊക്കെയാണ് ഉള്ളത് എല്ലാം. അല്ലെങ്കിൽ വാട്ട് ഈസ്, എക്സ്പ്ലെയിൻ, ഈ രീതിയിൽ തന്നെയാണ് ഉള്ളത്. അതുകൊണ്ട് ഡയറക്റ്റ് ക്വസ്റ്റ്യൻസ് ആണ് എല്ലാം ഇതിനകത്ത് വരുന്നത്. അപ്പം ഇതിന്റെ അറേഞ്ച് ചെയ്തിട്ടാണ് നിങ്ങൾക്ക് ക്വസ്റ്റ്യൻ ബാങ്ക് പറഞ്ഞിട്ട് ഇൻവൈസിൽ ഇട്ടിട്ടുണ്ട്. അപ്പൊ ക്വസ്റ്റ്യൻ ബാങ്ക് പ്രിപ്പയർ ചെയ്യുന്ന വേറെ ഒരു രീതിയിലല്ല. അതായത് നമുക്ക് 3 ക്വസ്റ്റ്യൻ പേപ്പേഴ്സ് ഉണ്ട്. ഈ 3 ക്വസ്റ്റ്യൻ പേപ്പേഴ്സ്, ഇത് സെക്കൻഡ് ക്വസ്റ്റ്യൻ പേപ്പർ, അതുപോലെ തേർഡ് ക്വസ്റ്റ്യൻ പേപ്പർ, ഇത്ര എണ്ണം ഉണ്ട്. ഇതിൽ എല്ലാത്തിന്റെയും ഈ ഒരു പാറ്റേണിന്ന് ഓരോ മോഡ്യൂൾ വൈസ് ആയിട്ട് എക്സ്ട്രാക്ട് ചെയ്തിട്ടേക്കുന്നതാണത്. അപ്പൊ അത് അതിനകത്ത് നോക്കി അറിയാം. ക്വസ്റ്റ്യൻ ബാങ്ക് ഓരോ മോഡ്യൂൾ 1ന്റെ കേസിലാണെങ്കിൽ ഒരു 12 ക്വസ്റ്റ്യൻ ഉണ്ട്. 12 ക്വസ്റ്റ്യൻ ഉദ്ദേശിക്കുന്നത് 1 and 2 കമ്പൈൻഡ് ആയിട്ട് ഒരു ക്വസ്റ്റ്യൻ ആയിരിക്കും ഫസ്റ്റ് ക്വസ്റ്റ്യൻ പേപ്പറിലെ. അതായത് 6 + 4 10 മാർക്സ്. ഇതൊരു ക്വസ്റ്റ്യൻ ആയിട്ടായിരിക്കും ഉണ്ടാവുക 1 and 2. അതേപോലെ 3 and 4 അടുത്ത ക്വസ്റ്റ്യൻ ആയിരിക്കും ഉണ്ടാവുക. അപ്പൊ അങ്ങനെ എല്ലാം കൂടെ സോർട്ട് ചെയ്ത് 12 ക്വസ്റ്റ്യൻസ് ഉണ്ട്. ഓക്കെ, ഫോർ മോഡ്യൂൾ 1. അപ്പം മോഡ്യൂൾ 1, 2, 3, 4 ഈ 4 മോഡ്യൂളിൽ നിന്നും കൂടെ 12 വീതം ക്വസ്റ്റ്യൻസ് ഉണ്ടാവും. ഇനി മോഡ്യൂൾ 5നും 6നും ക്വസ്റ്റ്യൻസ് കൂടുതലായിരിക്കും. അപ്പൊ അതിനകത്ത് പ്രയോറിറ്റി കൂടുതലുള്ള മോഡ്യൂൾസ് ആണ് 5ഉം 6ഉം. അപ്പൊ അതുകൊണ്ട് അതിനകത്ത് 18 ക്വസ്റ്റ്യൻസ് ഉണ്ടാവും. അപ്പൊ ഇവിടെ ചെയ്യുന്നത് എന്താണെന്ന് വെച്ച് കഴിഞ്ഞാല് നിങ്ങൾക്ക് ഓരോ ക്വസ്റ്റ്യൻസ് ആയിട്ട്, അതായത് 1 and 2 മോഡ്യൂൾ 1 1 and 2, അതേപോലെ 3 and 4 ഓരോ ക്വസ്റ്റ്യൻസ് ഓരോരുത്തർക്കായിട്ട് തരും. ഓക്കെ, അത് നിങ്ങൾ ചെയ്യേണ്ടത് വേറൊന്നുമല്ല, നിങ്ങൾ അതിന് വേറെ ഒന്നും എഴുതുവോ എഴുതി പ്രിപ്പയർ ചെയ്യണം എന്ന് ഞാൻ പറയുന്നില്ല. നിങ്ങൾ ചെയ്യേണ്ട അത് വൃത്തിക്ക് നോക്കുക. ഓക്കെ, നോക്കിയതിന് ശേഷം ചെയ്യേണ്ട കാര്യം പറഞ്ഞുതരാം. അതായത് നിങ്ങൾക്ക് ഗൂഗിൾ ക്ലാസ് റൂമിൽ ആ ടെക്സ്റ്റിന്റെ PDF ഞാൻ ഇട്ടിട്ടുണ്ടായിരുന്നു. ഓക്കെ, അപ്പൊ അത് സപ്പോസ് ഒരെണ്ണം എടുക്കുക. ഇതേപോലെ PDF ഉണ്ടാവും. ഓക്കെ, PDF ഉണ്ടെങ്കിൽ ഇതിൽ നിങ്ങൾക്ക് പറയുന്ന ടോപ്പിക് അല്ലെങ്കിൽ ഒരു ക്വസ്റ്റ്യൻ ആണെങ്കിൽ ആ ക്വസ്റ്റ്യൻ ആദ്യം വായിക്കുക. എന്നിട്ട് ചെയ്യേണ്ടത് നിങ്ങൾക്ക് ജസ്റ്റ് ഈ PDF നിങ്ങൾ ഓപ്പൺ ചെയ്യുക. PDF ഓപ്പൺ ചെയ്യുന്നതിന് കുഴപ്പമില്ലല്ലോ ഫോണിൽ. ഇനി സ്ലൈഡ് ഉണ്ടാക്കുകയൊന്നും വേണ്ട, അതിനുവേണ്ടി സമയം കളയുന്നില്ല. ആ PDF ഓപ്പൺ ചെയ്തിട്ട് ജസ്റ്റ് എടുക്കുക, ആ ടോപ്പിക് എടുക്കുക. ഇപ്പോ സപ്പോസ് okay, suppose you are asked to find the brakes of stopping distance. അപ്പൊ അതാണെങ്കിൽ നിങ്ങൾക്ക് ഈ ഒരു PDF ഓപ്പൺ ചെയ്യുക. നിങ്ങൾ ഓപ്പൺ ചെയ്തിട്ട് ജസ്റ്റ് ഇത് കാണിക്കുക. ഇത് കാണിച്ചുകൊണ്ട് തന്നെ നിങ്ങൾക്ക് എക്സ്പ്ലെയിൻ ചെയ്യാം. ഓക്കെ, അപ്പൊ ഫിഗർ വേറെ വരയ്ക്കാനൊന്നും നിൽക്കണ്ട. ഫിഗർ പറയാ, ഇങ്ങനെയാണ് ഇതിന്റെ ഫിഗർ, ഷൂ ബ്രേക്കിന്റെ ഫിഗർ ഇതാണ് എന്നൊക്കെ പറഞ്ഞ് ഇക്വേഷൻസ് പറയുക. ആ രീതിയിൽ എക്സ്പ്ലെയിൻ ചെയ്യുക. ഓക്കെ, പക്ഷെ ആ ഒരു ടോപ്പിക്ക് നിങ്ങൾ വളരെ വൃത്തിക്ക് തന്നെ നോക്കിയിരിക്കണം. ഓക്കെ, എന്നിട്ട് ഇത് ജസ്റ്റ് നോക്കില്ല. അപ്പൊ ഇതിന്റെ ഉദ്ദേശം വേറെ ഒന്നുമല്ല, എല്ലാം എക്സ്പ്ലെയിൻ ചെയ്യുന്നു. ഓക്കെ, ഓരോരുത്തരായിട്ട്. അപ്പൊ ആ ക്വസ്റ്റ്യൻസ് ഒരാൾ ഒരു ക്വസ്റ്റ്യൻ മാത്രം നോക്കിയാൽ മതി. അപ്പൊ ക്വസ്റ്റ്യൻ ബാങ്കിലെ 1 and 2 എന്ന് പറയുമ്പോൾ 10 മാർക്കിന് വരുന്നതായിരിക്കും. അപ്പൊ അങ്ങനെ ഒരാൾ ചെയ്യുന്നു. അപ്പൊ ഈ ഒരു രണ്ട് ക്ലാസ് മതിയായിരിക്കും ഇത് ഫുള്ളോടെ സോൾവ് ചെയ്യാൻ വേണ്ടി. അങ്ങനെ ചെയ്യുകയാണെങ്കിൽ എന്താണെന്ന് വെച്ചാൽ ഇത് നമ്മുടെ റെക്കോർഡഡ് സെക്ഷൻ ആണ്, റെക്കോർഡിങ് ചെയ്തിട്ടും ഉണ്ടാവും. അപ്പൊ പിന്നീട് പരീക്ഷയുടെ സമയത്ത് ഈ വീഡിയോ തന്നെ എടുത്തു നോക്കിയാൽ മതി. ഓക്കെ, അപ്പം നിങ്ങൾ തന്നെ അത് നോക്കുക. അപ്പൊ അതിന്റെ വിശദമായിട്ടുള്ള വിവരങ്ങൾ നിങ്ങൾക്ക് ഞാൻ വാട്സപ്പ് ചെയ്ത് തരാം. അപ്പൊ അത് നാളെ തൊട്ട് നമുക്കത് ചെയ്യാം. ഓക്കെ, അപ്പൊ ആരൊക്കെയാണ് ഡേറ്റും കാര്യങ്ങളൊക്കെ ഞാൻ തരാം. ഓക്കെ, ഓക്കെ, ഇപ്പൊ നമുക്കൊരു കാര്യം ചെയ്യാം. ഇന്നത്തെ ക്ലാസ്സിൽ നമുക്ക് എയറോഡൈനാമിക്സുമായിട്ട് 6th മോഡ്യൂളിൽ എയറോഡൈനാമിക്സുമായിട്ട് റിലേറ്റ് ചെയ്ത് തരുന്ന കുറച്ച് വീഡിയോസ് നമുക്ക് കാണാം. ഇതിനകത്ത് ഇവിടെ ഒരു ചാനലുണ്ട്, ഇവരുടെ ഈ കാണുന്ന ഇന്ത്യ എന്നൊക്കെ പറഞ്ഞ. അപ്പൊ അതൊക്കെ ഒന്ന് സബ്സ്ക്രൈബ് ചെയ്തിട്ടാൽ നല്ലതായിരിക്കും. കാരണം അതിനകത്ത് കുറെ കാര്യങ്ങൾ വരുന്നുണ്ട്. അതേപോലെ വേറെ ഒരെണ്ണങ്ങളുണ്ട്, ഞാൻ പറയാം. അതിനകത്ത് എയറോഡൈനാമിക്സ് മാത്രമല്ല, ഓട്ടോമൊബൈലുമായിട്ട് റിലേറ്റ് ചെയ്ത് വരുന്ന കുറെ വീഡിയോസ് വരുന്നുണ്ട്. അതൊക്കെ ഒന്ന് കണ്ടു വെക്കുന്നത് നല്ലതായിരിക്കും. കാരണം നമുക്ക് ഒരു എന്താ പറയാ, വീഡിയോ ആകുമ്പോൾ നമുക്ക് നല്ലൊരു ഐഡിയ കിട്ടും. ഇപ്പൊ നമുക്ക് ഈ PDF വായിക്കുന്ന അല്ല ടെക്സ്റ്റിനകത്ത് ഇപ്പം ഒരാൾ പറയുന്ന രീതിയിലായിരിക്കണം എന്നില്ല. കറക്റ്റ് ഒരു ഐഡിയ കിട്ടണമെങ്കിൽ ഇങ്ങനത്തെ കുറച്ച് വീഡിയോസ് ഒക്കെ ഒന്ന് ഇടയ്ക്ക് സമയം കിട്ടുമ്പോഴൊക്കെ ഒന്ന് കാണുക. അപ്പം നിങ്ങൾക്ക് യാത്ര ചെയ്യുമ്പോഴോ ഒക്കെ സമയം കിട്ടുമ്പോൾ എന്തായാലും ഫോൺ എല്ലാവരും കൈ കൊണ്ട് നടക്കുന്നതാണ്. അതൊക്കെ കാണുന്നത് വളരെ നല്ലതായിരിക്കും. ഓക്കെ,
before getting our teeth into aerodynamic effects and tricks. So in this video, that's what we're going to do. We're going to look at the building blocks of aerodynamics. A lot of it will at first seem removed from directly what you hear about what's happening across the wings and body of an F1 car, but these fundamental aspects will soon bring us neatly back to racing aerodynamics. We're discussing how we can affect the way air moves around. So we're going to look at pressure, what it is, how it moves around, and how it creates forces. We're also going to look at a key law of physical forces, and we're going to look at airflow. This video will set you up for everything we're going to look at aero-wise. So yes, it's a little bit of a physics lesson, but I brought a balloon, so it's fun. Stick with it and we'll wind our way back towards F1 as we head towards the end of the video. Pressure then, air pressure. what is it? You've probably got an intuitive sense of what air pressure is, but I'm going to explain it in terms of what's actually going on, so hopefully you can visualize it and understand it more fully. Air is made up of lots and lots of molecules all flying around inside the space the air occupies. We can think of pressure as kind of the busyness of all the molecules present in a particular volume of air. Pressure is basically the total momentum of all the little molecules flying around. To imagine this more clearly, let's think of a balloon. If we fill the balloon with air, the pressure of the air inside keeps the balloon inflated. Now, why is that? Well, all the particles in the air are flinging about all over the place, and naturally they bang against the skin of the balloon. Every time a particle hits the edge of the balloon, it pushes against it with some force. Now, multiply this force by all the millions and millions of molecules colliding against the skin constantly, and you can see it's enough to hold the balloon inflated. There are three main qualities that contribute to just how much pressure there is. One is how many molecules there actually are flying about the place. More molecules mean the air is much more busy, and in the balloon's case, there are much more collisions. We also have to think about how much space the molecules have to move around in. The air needed to hold a balloon inflated will certainly not work on something the size of a blimp. The number of molecules per volume is key here. We're asking how densely packed the air is. Thirdly, pressure is affected by the temperature of the air. Temperature actually refers to how much energy each particle in the air has. Higher temperatures mean the particles are more energetic and they're flying around faster. In our balloon, this means they'll be slamming against the inside with more force in every collision if the air inside is hotter. Aha, so you say, but there's also air on the outside of the balloon with all of its particles banging against the outside. Why don't these particles push the balloon inwards, deflating it? And the answer, of course, is that the air inside the balloon must be higher pressure than the outside. The forces pushing the balloon outward overpower the forces pushing the balloon inward. If the forces inside are significantly greater, the balloon inflates. And now we're starting to see how forces can be generated when air is at different pressures. Now, let's talk about what happens when we open the neck of the balloon. All the air rushes out, right? Now, bearing in mind what we just discussed, it's easy to see why this happens. The air pressure inside the balloon is stronger, so the air forcing itself out of the balloon is stronger than the air trying to force itself into the balloon. The result, the air rushes out. In fact, the air rushes out really fast because it's forced through a tight gap. The principle of airflow, described by the Venturi effect, notes that the smaller a region you force air to flow through, the faster the air will flow. Because you're still trying to push the same amount of molecules through, you've just got less space to do it, so it has to go faster. That's why squeezing the end of a hose makes all the water squirt out faster. You're forcing it through a tight space. As a very quick aside, in the balloon case, there's an extra element at play here. The balloon is elastic, so there is also a natural tendency for the stretchy skin of the balloon to want to deflate. But even if the air wasn't in a balloon, but in something more robust like a can, if we opened a hole between the high pressure inside and the low pressure outside, the air would still rush out. In fact, I just described how aerosol cans worked. So now we've understood how air flows from high pressure areas to low pressure areas if there's a space for a sudden high pressure area inside your mouth, which rushes out through the small gap you make in your pursed lips to the low pressure outside of your mouth. The result, fast, controlled airflow. Congratulations, you're an aerodynamicist. And now before we move on, I'm going to make sure we're all aboard with Newton's third law of motion. Now, some of you will know what this is already. If not, it's very simple. It's the one that goes, every action has an equal and opposite reaction. But what does this mean in the real world? It means if you push against something, it pushes back with equal measure. If I shove a sumo wrestler, I get pushed backwards. If a car crashes into a barrier, the barrier pushes onto the car and sends it ricocheting back onto the track. If a bird pushes its wings down on the air pushes back on the bird, causing it to stay in the air instead of falling. Inside the balloon, the particle pushed against the balloon skin, pushing it outwards, and the balloon skin pushed back on the particle, sending it bouncing inwards. Now, this may seem obvious, you may be saying. Why haven't I seen an F1 car yet in this video? You might be asking. Okay, so here we go. Here's the F1 car. Let's think about what the rear wing does. The rear wing's job is to force air upwards. But if the wing forces air upwards, there must be an equal and opposite reaction, right? When the wing forces air upwards, the air forces the wing downwards, and that's where downforce comes from. It's really that simple. Shove a load of air upwards, and the air will shove you down. Okay, but how are we shoving the air upwards? How does the wing achieve this? Now let's bring this all together. The wing profile is shaped a bit like this. Obviously, in real life, it's in 3 dimensions and doing all sorts of clever things, but in simple terms, it looks like this from the side. Now, At high speeds, in an ideal world, the air is going to come rushing at it in pretty much a homogeneous straight line. In fact, we can think of it as these nice layers of air. When the air hits the wing, some of it flows over the wing. These layers of air will scoot along following the curved surface of the top of the wing and exit out of the back. The rest of the air that hits the wing will go underneath the wing. This air has to take a much more aggressive approach to get under the wing, and you'll see here it gets squeezed between the wing and the wall of fast-moving air below. And as we discussed, squeezing air into a tighter space makes it go faster. So this air accelerates and travels under the wing at a much higher speed, following the curve of the wing and exiting at the back tip. So two things are happening here. One, the air under the wing is going much faster than the air over the wing. This means that the air under the wing is at a lower pressure. Why? Well, let's imagine the particles again for a second. When the air is accelerated through the squeeze, the particles separate out, much like a concertina effect you'll see with a train of cars leaving a slow corner. The faster moving air is more spread out, and as we covered, having less air in a space means the air has lower pressure. So, with low pressure under the wing and high pressure over the wing, we know, like with the balloon, the air above will be pushing harder on the wing than the air below. So the overall force will be downwards. And secondly, more importantly, look at the direction the air is going after it leaves the wing. It's going more upwards than when it met the wing. The wing has forced the air upwards, so in response, a la Newton's third law, the air has forced the wing downwards. A downward force is pushing down on the wing, and this is downforce. Naturally, if you tilt the wing further against the airstream in an angle referred to as the angle of attack, you'll force the air even further upwards and get even greater downforce. But this only works to a point, and we'll get onto that next time. These then are the basics of fast-flowing aerodynamics. But as you know, that's not the whole story. We haven't yet looked at why the airflow follows the shape of the wing underneath, and when it doesn't. This will lead into how wings can be inefficient, how air can stall, and where drag comes from. What is turbulence? And what are these vortices that you hear people talking about all the time? How do they arise, and how can they be in any way useful if we want nice smooth airflow? In the next video, we'll go a little more advanced and look at the more complicated airflow scenarios. Thank you for watching this video. Bear in mind, basics in pressure and flow, let's dig into the more F1 relevant parts of aerodynamics, how to control a wild and unwieldy airflow. Let's jump straight back to where we left off in the last video then, looking at our side profile of a wing with all the air flowing around it. So neat. It isn't always so neat though, and we'll get to that. But first of all, let's quickly work out why the air underneath the wing follows the surface at all. You see, if you imagine these layers of air rushing towards the wing all straight like this, the natural tendency for this air is to keep going in the direction it was. The underneath air will keep going straight, and this deflected air will keep going down, though the fast-moving underlayers of air should absorb this. So why does it, in reality, follow the surface of the wing? Because if there's no or very little air here, then it means this is a very low pressure area. And as we discussed previously, high pressure air will flow into areas of low pressure. So all this high pressure, high energy air is naturally going to bend into this pocket. Hi, I'm just going to stop the video here for a second and make a clarification on the last video. In that video, I said that the air under the wing moved faster because it was being accelerated by being squeezed. That's not the whole truth, and the majority of the acceleration actually comes from the air being pulled into that low pressure area. So sorry if I misrepresented what was happening there. Okay, back to the video. There's a second smaller effect going on here too, and that's the friction between each layer of air. It begins right at the surface of the wing, where the first layer of air particles actually doesn't really move at all because it's stuck to the wing by molecular forces. Each layer of air is attracted to each other. Between the basic static layer of air and the full speed layer of air here, each layer is moving a little bit faster due to the friction between each individual layer of air. This section is called the boundary layer. The amount of attraction or friction between layers of flow is called viscosity, The viscosity is one component of overall aerodynamic drag because the surface of the wing or car is tugging on the airflow, slowing it down, which means that, in turn, the airflow is tugging on the surface, slowing it down. Right, so we now know why airflow follows the form of a surface. Now I'm going to show you when it doesn't. Last video I tipped the wing up like this, increasing its angle of attack, and all the air followed it diligently. This will give you more downforce, I said. But actually tipping the wing up this high may well ruin everything and give you even less downforce. You see, if air is going fast enough, the momentum of the air may overpower the pull of the low pressure area here, and instead the air will mostly just plow on, being deflected only slightly towards the wing. This is called airflow separation or detachment. It should be clear that with the airflow separated, the average direction of the airflow after passing around the wings is less upward than if it all stayed together. This means that a separated airflow gives you less downforce than an attached airflow. Between these two flows of air, the air in between doesn't really know what to do with itself. The boundary layer will get sucked away from the surface and then get all garbled trying to resolve the pressure differences. This is called turbulence, and you may hear it referred to as turbulent flow, with the nice smooth airflow being called laminar flow, laminar just meaning layered. Right around the point where the airflow separates, the amount of downforce the wing delivers will drop massively, though the drag continues to increase. This is called a stall. So how do we resolve the problem of separated airflows ruining our nice efficient downforce? Well, we could just not tilt the wing so aggressively, but that's giving up. We need to find a way to keep this fast flowing energetic air attached to the surface for longer. And the answer is vortices. A vortex is just a spiral of air spinning like a screw along the airflow. So if we can imagine getting a vortex of air to flow between the attached boundary layer and high energy separated airflow, you can see how it can start bringing them together, pulling the high energy detached air into the boundary layer and allowing it to stay attached for longer while smoothing out the disturbance between the boundary layer and the separated flow. So in short, a vortex can help keep airflow attached to the surface it's flowing around. This doesn't just apply to the wing, but applies to the entire chassis too. Consider the car as a whole. We've got a number of places we want high energy, fast flowing air to go. The air intakes and the huge downforce generating rear wing, for example. But before the air can get to those places, it has to navigate the body of the car. And we don't want a separation in airflow to accidentally send a bunch of weak turbulent air into the rear wing or into the air intakes. Instead, we can use vortex generators to keep the airflow attached to the chassis and minimize the turbulent low energy flow. A further downside to air separation is that it causes drag. Imagine the car pushing through the fast flowing air. If the air separated dramatically behind it, this leaves a huge hole in the air of the car's wake, a massive low pressure area behind the car. Now with a high pressure area in front of the car and a low pressure area behind it, this causes a net force to act backwards on the car, dragging it back, reducing its speed. You can also think of the low pressure area creating a suction if that's easier. It's the same thing, if maybe slightly more clumsy way of putting it. Generating some vortices helps to attach scattered airflows to the body surfaces and reduces turbulence in the car's wake, which will reduce drag on the car. And I've been showing you a car side on, but this works in all dimensions. A lot of work is put into keeping the air attached right along the side of the car too, to stop the air doing this and to make sure it does this. In fact, one of the major jobs of the front wing, and the reason it always looks so complex, is to build huge vortices to help the airflow down the side of the car and to stop it getting mucked up by the mayhem caused to the air by the spinning tyres. All of the details and intricately sculpted tips of a front wing are designed in age of vortex generation that will help persuade the air in its flow all the way down the car. If we can take just one element to look at it, we can see how vortices are generated. So above the wing, we've got our high pressure air, and below the wing, we've got our low pressure air. Now, as we know, the high pressure air will try and flow into the low pressure air to resolve the difference, and it doesn't have to wait until after the air has passed over the wing to do it. At the edge of the wing here, the top flowing air will try and curl over the wing and get to the bottom flowing low pressure air. From here, we can see how a corkscrew movement starts at the wing tip and will continue down the chassis. All of these wingtip shapes will work together to create a really huge vortex that doesn't just help keep the good airflow follow the shape of the chassis, it also helps keep the bad airflow, the disturbed turbulent air in the wake of the spinning tyres, away from the bodywork to stop it ruining everything. These vortices are the bouncers of an F1 car, telling the drunk tyre airflow to keep on moving, sir, keep on moving. So that's the basics of how you control airflow and coax it into doing exactly what you want it to do. The next video will be a bit of a free-for-all on little aero bits like what does this thing do, why are there holes here, what's a barge board, that kind of thing. Thanks for watching this video. It was quite short and cheerful, but I really wanted to get into the heart of what vortices were as they're discussed so much in aerodynamic chat. Next week I'll probably do the last part of this short aerodynamic series, but continue to do videos that touch on aerodynamics in future. Thanks so much to everyone who continues to support me doing these videos. I've managed to not have to leave an extended To complete our three-part mini-series on the various aspects of aerodynamics, I'm going to look at a few common aero devices. I'd suggest you look at my previous two videos on aerodynamics, as I'll be assuming you know the basics I sort of rattle through. Looking at the rear wing then, there are two devices on the end plates that all cars use now. One is these little slots or louvers. The other is this cutout behind the actual wing itself. What's the deal with these? Well, first, let's understand why end plates exist in the first place. Without them, you get big old vortices generated by the high pressure air spiraling out into the low pressure air below. Now, I talked a big game on vortices in the last video, but there is a negative byproduct to them, drag. What's happening is this. Before the vortex is generated, the air is going straight backwards. In generating a vortex, you're taking some of the backwards going energy and turning it into a sideways spiraling energy. That is, the air is losing some of its backward speed. You're slowing it down. And if you slow air down, the air slows you down. That's drag. So to reduce vortex generation, they simply bang massive panels on the edges of the wings, the end plates, and this stops the air spiraling over and creating vortices. But the air inside the end plates and over the wing here is much higher pressure than the air outside of the end plates here. So at the wingtips here, the high pressure air still rushes over the top to find the low pressure air, causing wingtip vortices, which are a bit draggy still. So to combat this, these louvers allow the high pressure air to mix slightly with the air outside of the end plates and reduce the pressure difference. And to explain the cutout at the back, realise now this flow of air outside the end plates is actually a higher pressure than the air under the wing inside the end plates. So this generates a little vortex itself, but as it's spinning in the opposite direction to the wingtip vortex, it neutralises the overall spin and reduces its effect. Moving below the rear wings now, let's look at diffusers. The diffuser is the big scoop-shaped thing at the rear of the car floor. To understand the diffuser, let's look at the car from the side and cut everything else away. Now we can see the diffuser helps the underfloor of the car become a lot like the underside of a racing wing. The air rushing under the car is crammed into this tight space between the car floor and the track. The diffuser, like the exit curve of a wing, sucks the air into this low pressure void here, and this suction essentially continually accelerates air through the tight undercar space. As we learned previously, squeezing and accelerating air massively reduces the pressure of that air, and this low pressure area sucks the car towards the ground. This is a huge downforce generator using what's known as the ground effect. The shape of the diffuser works hard to smooth out the airflow as it transitions from fast low pressure air to the ambient air behind the car. In fact, often the whole car is raised from back to front, increasing the angle of what's called the car's rake to smooth out this diffusion process right along the car. The vertical straights also work to guide the air smoothly out of the back of the car, increasing the efficiency of the diffuser and reducing turbulence. Now let's look at barge boards. There's a lot going on with barge boards. You could spend an hour trying to unpick all the nuances of any individual barge board, but I'll try and keep it simple. Firstly, they work to deflect and shape the path of different airflows. Alongside the car, you've got nice smooth flowing air alongside the body, you've got this big vortex powering out the front wing, and you've got dirty air from the tyres, all very messy and horrible. The vortex is something of an impenetrable high energy wall, so part of its job is to keep the messed up tyre wake away from the nice smooth airflow running along the body. The barge board helps coax the vortex around the body of the car and allows the clean air to pass on through to places like the air intake and around the body. Secondly, the shape and intricacies of the barge board and the turning vanes, which are just elements very similar to the barge board but situated further up the nose, create their own vortices, which help seal in the fast, low pressure air under the body, stopping it leaking out, which would reduce its effectiveness. Older cars used to have actual physical seals at the bottom of the car called skirts, but these were banned long ago when the ground effect was getting too strong. So barge boards and turning vanes direct the complex flows of air and generate a vortex seal along the base of the car to aid the air travelling to the diffuser. And finally, let's explore the S-duct. On some cars, you'll be able to see the entry point of the S-duct, visible as nostrils on the nose of the car. And on some cars, you'll see the exit point, a letterbox opening on the bridge of the nose, just in front of the suspension. The S-duct channels air from under the nose up to the top surface of the nose here. This solves two problems at once. Problem the first, the boundary layer, the layer of air slowed down by frictional forces of the car's surface, can build up here, causing drag and pressure problems. Allowing it somewhere to escape can relieve this buildup. Problem the second, the slope of the nose can cause some airflow separation, which we saw in our last video. As we know, this is inefficient and draggy. Blowing air across the surface energizes the boundary layer here and keeps the air smooth and attached to the nose as it travels down the body. Overall, it's a small effect, but it's a net gain worth exploiting. Look all over any given F1 car and you'll see lots of little devices all guiding air, affecting pressure differences, or trying to minimize error effects altogether. Hopefully, with the help of these 3 videos, you'll have a better foundation on which to understand all these bits and bobs all over the cars, have more of an idea of the effect of the new aero developments in future, and understand all the jargon that TV presenters and articles use when talking about aero parts. This isn't the last I'll talk about aerodynamic parts and effects in future, as there seems to be no end to the weird little exploits the engineers will invent to make airflow bow to their whim. Thanks for watching this video. The F1 season is starting very shortly and I'm going to start working on some ideas for
നിങ്ങളുടെ അറ്റൻഡൻസ് ഒന്ന് പറയണേ.